Hello students, and this is your lecture for Chapter 7 regarding measuring and evaluating human energy generating capacities in physical activity. This particular chapter talks about many different concepts in regards to some things that you've already heard of before in regards to VO2 max, exercise testing, the energy systems, things of that nature. So without further ado, we're going to go ahead and jump right into it. Don't forget to go back and make sure that you're familiar with the chapter objectives, at least after you've finished listening to lecture and reading through the chapter. So all individuals possess a capability for anaerobic and aerobic energy metabolism, yet the capacity for each energy transfer form varies considerably among different individuals. So a person's capacity for energy transfer really depends largely on a couple different things, activity mode and training status. So for activity mode, we could be discussing something like swimming, walking, biking, running, different modalities. Training status, obviously, if someone that's been doing running for a very long time, or someone that's participated in a lot of 5Ks or endurance events like triathlons would be considered someone who has a trained history versus somebody that's untrained, like your sedentary population that doesn't do a whole lot of physical activity. So again, the capacity for the capability of the anaerobic and aerobic metabolism is present within all of us, but it varies greatly according to activity mode, what we're doing, and someone's training status. It is possible that one person could have a very different VO2 max from one modality to the other. So the example that you see here on the PowerPoint is swimming versus running. And that has a lot to do with, again, the trained status. If you're an avid swimmer and you're asked to do a VO2 max assessment on a treadmill and you're asked to run, you may very well have a different performance because of the familiarity, because of the lack of exposure to practicing running over and over again. So this is what we kind of refer to as the specificity of metabolic capacity. And this represents the fact, again, that some people can have a high VO2 max in one particular activity, and they can also have a very high VO2 max for another mode. So when your book talks about specificity of metabolic capacity versus the generality of metabolic capacity, typically, for the most part, more specificity exists than generality in metabolic and physiologic functions. So in other words, you're usually going to see individuals that can have a high VO2 max for walking, but then might have a lower or not as efficient VO2 max for, let's say, running. And what you can see on this slide illustrates the specificity generality concept of energy capacities. The non-overlapped or the single color areas of the red, the blue, and the green represent specificity of physiologic and performance functions, while the overlapped areas with a blend of 4 adjacent colors represents the generality of functions. For each energy system, specificity exceeds generality. Very rarely do individuals excel in markedly different activities. For example, sprint running and distance running. Both activities involve running, but their physiologic and energy system requirements differ remarkably. Many world-class triathletes seem to possess generalized capacities for the diverse aerobic activities, yet their high performance levels result from thousands of hours of high-specific sports and performance training in each of the triathlon's 3 demanding events. Based on the specificity principle, training for high aerobic power contributes little to one's capacity for anaerobic energy transfer and vice versa. The effects of systematic physical training remain highly specific for neurological, physiologic, and metabolic responses. Since a majority of this chapter is about measuring and evaluating the energy systems present, I just want to take an opportunity to review some of the concepts that we've learned prior to this chapter in regards to the ATP PCR immediate energy system, the anaerobic glycolysis energy system, as well as the aerobic glycolysis system. So this picture represents the 3 systems of energy transfer and the percentage use of their total capacity during one's all-out physical activity of different durations. So again, you can see here that immediately we depend on our ATP PCR, our high energy phosphagens present, and we utilize those immediately, and we only use those for a very short amount of time before that supply or that energy system is tapped out. At that point then, our short-term or our anaerobic glycolysis kicks on and takes over for about 2 minutes worth of duration. And at that point, that system begins to fade off, and our long-term, our aerobic glycolysis energy system, the final system, begins to kick into place. Okay, so jumping into part 1 of chapter 7 looks at different assessments to really analyze and better understand when our immediate energy systems are in use. So we have physiologic and biomechanical measures that include, first, measure changes in the levels of intramuscular ATP PCR pool, or also the lactate produced from any sort of anaerobic metabolism. And by the way, this is the most direct assessment that correlates highly with performance assessments. So you'll understand what that means in just a second. But it also includes measures to look at the depletion rates for an all-out brief, short duration typical activity. This is usually done through taking muscle samples. And yes, it is absolutely as unpleasant as it sounds. There's things called a muscle biopsy where they make an incision. Typically, the muscle biopsies are done in the quadriceps muscle, usually the vastus lateralis, maybe even the rectus femoris. But they make an incision over the muscle. They take a small, it kind of looks like you're getting a needle shot, a cannula, I guess is a better word for it. And it's actually plunged deep down into the muscle. And when the cannula retracts, it pulls up a small kind of hamburger piece size tissue sample, and then they can analyze that to look at depletion rates. They can also use that particular sample to see current levels, and then what they can do then is kind of compare pre-existing levels to depletion rates when it comes to post-activity muscle samples. And yes, if they took the sample at one point in the leg, they would also take an additional sample at that same point in the leg again to look at any sort of depletion rates. So you'll hear me talk about muscle fiber sampling later on as you develop into the program. But again, both approaches assume that there's a short duration intense activity that absolutely cannot occur without this high level of anaerobic energy transfer. And then the measurements can gauge anaerobic energy utilization. So these are some performance tests of short-term glycolytic power. Remember, when we're talking about the short-term glycolytic power, we are talking about the high energy phosphagens with the presence of ATP and phosphocreatine and their depletion rates. These are the high energy phosphagens that are present in these max assessments that usually last 1 to 10 seconds and reflect the energy transfer of the immediate energy system. And we're able to quantify external work performed and the power that's generated. Different types of assessments include any sort of jump power tests, sprint running or cycling, shuttle runs, arm cranking with maybe like an upper body ergometer, and then also assessments that simulate stair climbing, rowing, skiing, running, things of that nature. If you've ever seen the tests that they run for an NFL combine, they look for a vertical jump assessment. They want to see how high somebody can jump. They want to see a 40-yard dash and understand the time associated with that. So even though this is definitely related to sports, these are also excellent examples of immediate energy power assessments that can be done in the field. And a lot of those assessments measure power, or the output of power, that really looks at the time and the rate of the work that's being performed. So usually these performance tests look at maximum effort in a short amount of time, usually within about 1 to 10 seconds. For whatever reason, guys, I haven't been able to successfully show the videos that have been linked to these PowerPoints through Screencast-O-Matic. So I can't click on them for you because I've actually had to go back and redo it several times, or do the voiceover several times, because there's an issue with the voiceover and the background music and the audio coming from YouTube. So you have access to these PowerPoints. I would encourage you to get into the PowerPoints and click on the videos. The first video is a really good video showing some of the assessments done for the sprint power assessments. Power can be reflected in different units of energy. So this is just a conversion chart for you to refer to if you come across any formulas that require you to convert numbers. Remember, there's a low interrelationship among different power output and capacity test scores, which means there's a high degree of task specificity. Again, that goes back to typically individuals who are trained in a certain sport will have a great VO2 max. Their systems will be very trained for certain blood lactate levels and for certain abilities regarding power output according to the training that they are familiar with. So this brings up kind of a good next point, that athletes need to test how they are trained. As a coach, I tell my players, you need to practice how you will play because that is indicative of your performance on the field. Similarly, to the comment or to the idea that athletes need to test how they are trained, that means if we're testing football players, we need to make sure that we're testing them on the same surface that they're going to be competing on. So if they play on a grass field, we need to test them on a grass field. If we have basketball players that wear rubber-soled sneakers and perform on an athletic indoor court, we should be testing our athletes on an indoor court because this is a more true assessment that accurately reflects either their power output, the depletion levels of their intermuscular high-energy phosphagens, and things of that nature. I just want to review for a second. When we're talking about the immediate energy system, scientists or researchers measure the high energy phosphagens ATP and PCR, and also the depletion rates that are present through muscle sampling. The process to understand or to assess the indicators of short-term energy system that you see on this particular slide is a little bit different. So now we're moving beyond the activities that last only up to about 10 seconds. We're moving on into the next or the second energy system, which is still anaerobic in nature, but now it's referred to as the short-term energy system or also anaerobic glycolysis. Scientists study the accumulation of lactate, and they also look at muscle glycogen levels when trying to assess activity within the short-term energy system. There is no single criteria that exists to truly indicate when a person reaches their maximum anaerobic effort, but we do know that it's typically related to the effort and their participation. Self-motivation also has a lot to do it, and also several external factors. Blood lactate levels. Understanding blood lactate levels, we understand that they accumulate from this glycolytic energy pathway activation during short duration, maximum all-out physical activity. And establishing one's blood lactate levels reflects the capacity of an individual's short-term energy system. So again, another indicator of the switch on, that dimmer switch turning on in the short-term energy system, anaerobic glycolysis, is understanding blood lactate levels. This is done through blood sampling, actually blood draws. So you can starting to understand why a lot of researchers, this is done in a lab setting or in a very clinical setting, because muscle biopsies and blood draws are not something that you can just do in an everyday classroom. You have to be trained for it, especially with blood draws. You need to be certified in order to avoid any issues with doing it appropriately, safely, and also making sure that you are safe in that instance as well. The other indicator of short-term energy system is the glycogen depletion. Remember, we've talked about the circulating blood glucose levels as well as the stored intramuscular glycogen levels. And the reason that we talk about that is because the short-term energy system depends on glycogen stored within our specific muscles that are activated by exercise beyond that 10-second mark. So the pattern of glycogen depletion in specific muscles indicates the contribution of glycolysis to physical activity, and that is another physiologic method to understand what energy system a certain athlete is working on, or in, sorry. When looking at blood lactate levels, your book points out a study that was done regarding some cyclists, specifically 10 riders, who were asked to pedal on a stationary bicycle ergometer at their highest power output increases in order to increase their blood lactate. So what you see here is the test duration in seconds and the blood lactate levels rising as a part of their efforts and as they increased. So the researchers actually did blood draws prior to the actual intervention. After they took the blood draws, they asked the experienced riders to get onto the bicycle. They explained the protocol, and then they began the initiation of the assessment. And you can see again, as the duration of the assessment got longer or lasted, you could see a rise in blood lactate levels. And what you can see on this particular graph is plotted averages of all 10 riders. So what can we draw away from this? The increase of blood lactate as intensity, not necessarily intensity, duration goes up. We have no indication, according to what we see here, that intensity is increased. Intensity might be a secondary factor due to the increased duration of the assessment. This graphic that you see here shows you the relative contribution of each energy system to total work in 3 short duration assessments. So I like the top because I understand percentage of total work a little bit more than I really understand kilojoules, but it is an expression of power. So I'm going to describe the top first. This is kind of another representation, guys, of the energy systems that are present. So you can see the longer you work, the different energy systems that switch on. Again, you can see that the 3 of them work in conjunction with each other. One is never completely turned off. One is never completely dominating. They are all working in tandem. It's just in different strengths per se, according to the duration of the assessment. So you can see initially right off the bat with an assessment, we have our high energy phosphagens that are present in this immediate energy system that's taking place during just a few seconds of work. And then as our work load increases according to time, then we have this anaerobic glycolysis that takes over. And you can see that transition here happen over the time. So this is an indication of time here at the x-axis. Again, the y-axis is the percentage of total work that takes place. So short activities, you can see ATP-PCR is dominant, as well as a little bit of a switch over to anaerobic glycolysis with very little contribution coming from the aerobic glycolysis energy system. And again, you can see the switch happening the longer that we continue to perform work, with finally ATP-PCR actually putting forth very little contribution, a little bit, but not much, as the aerobic glycolysis really takes over. We've been able to look at lactate accumulation as it occurs over an exercise duration, and now we need to also understand to look at the glycogen depletion level, because again, this is the second way that researchers can measure or look at short-term energy system as it occurs. This particular graph is, again, we're looking at glycogen depletion from the vastus lateralis, that's the muscle from your quadricep, during cycling of different intensities and durations. So this is still a cycling assessment done by different individuals, and they asked the different individuals to work for a very short amount of time at a very high intensity, and then they manipulated it and had another rider, again, run at 120% of their maximum capability, again, for a little bit longer of a time. And you can see for each one of these graphs that their time was increased, and with that, they were only asked to do a certain portion of their absolute maximum capabilities. So the energy derived from the short-term energy system really depends on the glycogen quantity stored within the specific muscles that are activated by physical activity. In this case, we are talking about probably a lot of lower body muscle glycogen being present. And also, guys, we can't truly understand the glucose and the glycogen storage amounts because a lot of that depends on previous rest, previous diet intake, right? If they had had a decent meal 3 to 4 hours before their pre-competition event, with adequate amount of macronutrients present. So we can understand a pattern, but these initial levels that you see here is simply something that was measured by the researchers, probably from doing a blood draw. And again, that varies from athlete to athlete depending on their previous training, if they worked out prior to this particular study, a whole lot of different factors that can affect that. But what you can see is activity at only 31% of their VO2 max, which represented the lightest load tested, caused a little bit of depletion, but the most rapid depletion of muscle glycogen levels occurred between 83 to 150% of someone or an experienced cyclist's VO2 max. So the harder you work, the faster your muscle glycogen storages deplete. Short-term energy system activation occurs in maximal work for up to 3 minutes in duration, and testing this energy transfer capacity usually involves an all-out run or some sort of all-out cycling, including resistance training using repetitive lifting of a certain percentage of either their maximum or shuttle and agility runs. So I've listed just a couple that are very common in the industry, such as cycle ergometer tests. The Wingate test is something that's very common. It's very well respected. It's also used a lot. If you simply put in Google Wingate test, or if you go to YouTube and put in Wingate test, you'll see just how much fun they appear to be, and probably are even more fun to actually be the participant in. Other examples of this type of field test would be any sort of sprinting events between 200 to 800 meters. An 800-meter dash is 2 laps around a normal track. It could also incorporate the 400-meter dash, which is 1 lap around. And then there are also several types of sport-specific run tests. There are 5 factors that impact performance on such tests, and we're going to talk a little bit about each of these here in the following slides. So the first one that we're going to talk about, we're going to talk about the Wingate test first. Okay, so before we talk about those factors, let's talk about peak power that's measured on a Wingate test. And a catch test is a very similar format, but they measure the highest mechanical power generated by the subject during any 3 to 5 second period. Typically, the test lasts for as long as you possibly can go. And the anaerobic capacity denotes a total work accomplished over 30 seconds. So we have a relative power that represents peak power divided by body mass. So that's why you see here that body size can be a factor that impacts performance on these types of tests. But anaerobic fatigue represents the percentage of decline in the power output that you see as the duration of the test lasts. So the rate of fatigue corresponds to a decline in power relative to the peak value, or the most that they're able to perform at. So these tests assume that peak power output reflects energy generating capacity of these high energy phosphates, while average power reflects more of the glycolytic capacity. So again, when we're talking about these peak performance assessments like the Wingate or like the catch test, again, these tests assume that peak power output reflects the energy generating capacity of our high energy phosphates. Again, that's our ATP and PCR, while average power that is expended during an assessment reflects more of the glycolytic capacity. Okay, so let's talk about a couple of the factors that can affect power. Let's talk about children. Children have a reduced capability of producing anaerobic power. You cannot expect for an adult and a child to perform in the same manner on a Wingate assessment. Children actually perform poorer on tests of short-term anaerobic power compared with even adolescents and even young adults. And the reason being is that our children have smaller, less developed leg muscles. What does this mean? They have less power producing ability than adults, which means that children's lower muscle glycogen concentrations and the rates of glycogen utilization are not as comparable to adults. So that is why Children that are sprinting, they basically have less power output than their adult counterparts. And it has to do with muscle size and also lower muscle glycogen concentrations. There are also gender differences in anaerobic power. So there's a couple different things. We have differences in body composition, differences in physique, muscular strength, or neuromuscular factors. They don't fully explain the considerable differences that are present in anaerobic power capacity between men and women. Studies do suggest the possibility of gender-related biological differences in anaerobic capacity, and unfortunately, your textbook doesn't really go into that much more reasoning. Other factors that affect anaerobic power, again, specific training. If an athlete has gone through short-term or super maximal training, this actually produces higher blood lactate levels, as discussed earlier in class, and it also higher depletion of those muscle glycogen levels. So remember, the higher blood lactate levels generally indicate a more trained individual. And that's a good thing because, remember, blood lactate is trainable, usually with sedentary populations whose bodies hasn't made that physiological adaptation will suffer more and not be as comfortable in their training regimens as the individual who has practiced over and over and again. Their body has an opportunity to physiologically adapt and allow that increase in blood lactate level. So what that means then is that they're basically delaying or pushing further the rate that fatigue sets in. Another factor affecting anaerobic power then is the buffering of acid metabolites. So this increases the body's ability to buffer, but it's not totally proven by science yet. So kind of keep that idea with a pin in it. Motivation also has a lot to do with a performance test. If you took an opportunity a minute ago to pause and Google and look up the Wingate test, you will have seen that typically someone taking a Wingate test is not simply on the bicycle ergometer by themselves. This test is utilized frequently in university settings with sports teams in the athletic department. They'll use it to test the basketball team. They'll use it to test the glycolytic power of maybe even the football team. And you'll notice that as each athlete steps up to take the assessment, they've got a crowd of people around them yelling at them, go, 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 you can do it, keep working, don't let down. It also has to do with the athlete's inner motivation as well. And if you imagine, if you can think about it, if you're a very trained individual, you're going to have a greater tolerance for pain or discomfort because you have this increased ability to push beyond something like fatiguing physical activity. So those cyclists that have very specific training regimens where they're on their bike constantly, not only are they going to increase their amount of lactate present within the blood, but they're going to be able to manage that pain, manage that discomfort, and go beyond that fatiguing effect. So motivation does have quite a bit to do with performing a test that looks to understand glycolytic power. Okay, so part 2 of chapter 7 is how to measure and evaluate our aerobic system, the third and final energy system present within the human body. And there's a couple different methods that we do this. There's direct calorimetry methods. There's also indirect calorimetry methods. So we're going to be going over those particular processes. All metabolic processes ultimately result in heat production. It comes from cells, tissues, whole body operations that occur. This measurement defines the energy metabolism rate. So we measure that in the form of the unit form of kilocalories. And so the measurement of kilocalories is called calorimetry, and this refers to the measurement of heat transfer. So there are two different measurement approaches. We can measure that directly by actually putting a human being in a closed room and measuring the temperature that rises according to physical activity, or if that is an inconvenient way, to measure an athlete's heat production. Obviously, sticking them in a room and leaving them in there for a long time and making them do physical activity isn't always ideal. So then we can use the indirect calorimetry method with more portable devices. This is a great picture defining the metabolic processes that happens when we intake our food, when we have this exchange between the oxygen and the carbon dioxide, and also when we are adding water into the mix. So this is a measurement of the body's rate of heat production, and we directly are able to assess the metabolic rate. It can also be estimated indirectly by measuring the exchange of carbon dioxide and oxygen during the breakdown of food macronutrients, and also through nitrogen excretion through the urine. So this is what direct calorimetry looks like, specifically a bomb calorimeter. So if we were simply measuring the heat energy produced by foods that we consume, what we do is we actually take a very small sample of that particular food item and we put it in this sample cup right down here at the bottom. And then the machine will ignite. There's basically a switch that is hit, and with that ignition, the food literally explodes within this chamber. And then this surrounding sealed bomb obviously absorbs the heat, and that heat is then therefore transferred into the water that surrounds that particular chamber. And if you notice over here, we have a thermometer, and that's how we can measure the heat production of the food that we eat. So a direct calorimeter can assess human energy metabolism by measuring the heat production, very similar to this method that you see here through bomb calorimetry. So if you can imagine actually putting someone in a closed environment, it doesn't sound like a very fun process, especially if you're claustrophobic. So obviously we can't cause humans to ignite and measure the temperature, but what we can do is put them in something called a human calorimeter. So yes, in very early studies, when technology wasn't so accessible, early researchers actually created rooms where they would stick a participant in an enclosed space, and usually there's a treadmill, or like you can see in this particular picture, there was a bicycle, and they were to perform work. And obviously, when we begin to perform work, we begin to inhale and exhale. We have that exchange of gases that takes place, but we also are producing heat, and our body's response to that is to sweat. So this heat, through the activity happening by this person, would then actually heat the room itself, and that's why you had these copper coils up here that would measure, or have a thermometer in it, that would measure how much the temperature rose through the activity that was taking place inside this room. So they had a way to vent it. You can see all that down here. This particular human calorimeter did not necessarily directly measure the intake, the inspiration and expiration of gases, but they did that through the filtering system down here with our oxygen supply. So again, they stuck somebody in a room and asked them to do work. If you don't like small spaces, or if you don't like being in a calorimeter for a very long period of time, this might not be the study for you. The link that you see at the bottom of this page actually shows a participant. I believe she had to live in there for something like 12 hours or maybe even 24 hours or more. They were basically measuring her heat output during sedentary behaviors as well as physical activity behaviors. But this is not as commonly used method to evaluate our aerobic system anymore, because think of how many people would volunteer, how many professional athletes would say, sure, you can stick me in a room. Not a lot of people would go for it. So we have other methods through indirect calorimetry, and this is measuring a person's VO2, or their consumption of oxygen expiration of carbon dioxide, to provide an indirect yet very accurate estimate of energy expenditure. So I'm going to go through some of those techniques for you right now. We first have something called a closed circuit spirometry device. And this is typically unsuitable for use during physical activity where the subject moves around a lot or expires large air volumes. mostly because they have to be hooked up to a machine. So then we can utilize an open circuit spirometry method that I'm going to show you here. So we've got a bagging technique, we've got the portable spirometry, which is kind of becoming more popular, and we'll take an opportunity to explain to you the computerized instrumentation as well. So this is the closed circuit spirometry method. You can see here that someone has to be breathing in and out of this mouthpiece down here next to this very large tank, and a subject will inhale ambient air, take a very deep breath, and then they'll actually exhale right here into this mouthpiece. And then through the processing, a computer will calculate the volume of air inhaled and expired. And they also measure it according to the time and the composition of the air to oxygen uptake. So the computer will read it, and then it will basically be able to talk to you or give you a score in regards to your aerobic system pertaining to your VO2 max, probably. Again, with this particular method, you can see that for athletes or someone being very physically active, it would be very hard to use this particular method because of how large the equipment is. And this is also a picture, so it's not exactly exact in its proportions. But it is something that it would not be very portable. So we had some updates, some technological advances that were made, and this is called the bag system. So this is an example of the open circuit spirometry. So you can see that now we have an athlete that's able to perform work. They're on an ergometer, but now they're actually wearing some sort of oxygen mask device. And you can see that the expired air will pass through this mask into the diaphragm that you see here, and it actually goes through a meter that can measure the flow. So there's an aliquot of expired air. It is then analyzed, and they look at the oxygen versus the CO2 composition as well. And then again, a computer system calculates the VO2 and also can calculate caloric expenditure. Pretty old picture, you can tell by the mustache and the sideburns. You're also kind of able to see kind of the technology evolving to make this a better tool for active populations. So here's a new and improved method of indirect telemetry. And this is the portable open circuit spirometry. And this has basically a pack that is strapped onto the athlete's back, kind of like a backpack. They still have this device that directly measures their inspiration and expiration. And so this has got that kind of like built-in CO2 and O2 analyzer. You would imagine this is not a very cheap device, even though it is much more new and improved. We can actually have cyclists tested in the field as opposed to having to be in a clinical situation that you can see here. So again, when we're talking about being specific with our assessments, specific with our training, we want to try and assess our athletes in vivo, wherever their competition truly may be. So you're more likely to get accurate assessments and accurate test scores when you're able to actually have a cyclist go out and ride on a course that they would typically ride during competition. There's also something called the doubly labeled water technique, and this is where a subject consumes a quantity of water with a known concentration of a heavy, non-radioactive form of stable isotope of heavy hydrogen. Wow, that's a mouthful, isn't it? Basically, what happens is the subject consumes this quantity of water, and the isotopes distribute through all bodily fluid and eventually leave the body as water, usually right around 5 hours. So it can leave in sweat, it can leave in urine, it can also leave in our pulmonary water vapor that we exhale when we breathe out. And researchers record how long it takes for the isotopes to leave the system. So they do a pre-test, they do a post-test, they measure how many isotopes until they don't see isotopes present within the system anymore. So this is an isotope-based method that safely estimates total daily energy expenditure in free living conditions without any normal constraints imposed on by laboratory procedures. So we get kind of started by talking about this room that you were put in for direct telemetry, and then you could see the evolution with indirect telemetry with that system that you had to breathe into, to that huge portable bag, or not portable, but that huge bag in a laboratory setting that you had to breathe into, and now into this basically backpack spirometer that measures. But now think about just simply relying on the doubly labeled water technique, where there is no equipment. You simply consume a fluid, and your scientists and researchers can record how long that isotope is present within your body. So this could serve as criterion or a standard to validate other methods that estimate total daily energy expenditure over prolonged periods. Another method of measuring the aerobic glycolysis system, or our long-term energy system, is by understanding a respiratory quotient. Complete oxidation of a molecule's carbon and hydrogen atoms to carbon dioxide and water end products requires different amount of oxygen because of inherent chemical differences in the macronutrient composition. So again, that's our carbohydrates, our lipids, and our proteins. Consequently, the substrate metabolized determines the quantity of carbon dioxide produced relative to oxygen consumed. So the respiratory quotient refers to the following ratio of metabolic gas exchange, and that's the formula that you can see listed right here for you. The respiratory quotient helps approximate the nutrient mixture catabolized for energy during rest and aerobic physical activity. Also, the caloric equivalent for oxygen differs depending on other nutrients oxidized. So precisely determining the body's heat or kilocalorie production requires information about both oxygen uptake and also respiratory quotient. What I want you to get from this section in the book, because it can be very confusing and very difficult to understand, is simply understand the respiratory quotient for the different macronutrients. So the respiratory quotient for carbohydrates is 1, lipids is 7/10 or 0.7. Lipids kind of range between 6900s and 7300s, truly really depending on the oxidized fatty acids carbon chain length. The respiratory quotient for protein is 8200s, and for a mixed diet, it's the same. And this is from the metabolism of a mixture of about 40% carbohydrates and 60% fats. Please don't spend a whole lot of time fretting of or rereading this information. I just want you to understand again, the respiratory quotient is the ratio of carbon dioxide produced to the oxygen consumed with complete oxidation of a nutrient measured during steady rate metabolic conditions. So we understand that we are not always participating in a steady rate metabolic condition. Sometimes we are working at a very vigorous intensity, and so that would throw off having a calculation in regards to your respiratory quotient, and here's why. Application of the respiratory quotient requires the assumption that oxygen and the CO2 exchange measured at the lungs also reflects cellular level gas exchange from nutrient metabolism. Again, this assumption remains reasonably valid for rest and steady rate light to moderate aerobic physical activity conditions because there's a minimal lactate accumulation for these particular activities. Remember, various factors can alter the exchange of oxygen and carbon dioxide in the lungs, so then gas exchange ratio no longer really reflects only the substrate mixture in cellular energy metabolism. For that purpose, just understand the respiratory quotients that you see on this page, or the percentages that you see reflected here. Another way that we're measuring aerobic glycolysis is through the respiratory exchange ratio. R, or RER, represents the carbon dioxide elimination during physical activity. So remember, the respiratory quotient is best for steady rate activities. This particular letter or value is best utilized with physical activity. And here's an example why. Carbon dioxide elimination increases during hyperventilation because our breathing increases to disproportionately high levels compared with intrinsic metabolic demands. So by us overbreathing through hyperventilation, the normal level of carbon dioxide in our blood decreases because the gas blows off in expired air. And a corresponding increase in oxygen uptake does not accompany this additional CO2 elimination. So consequently, the exchange ratio often exceeds a 1.00 value. Respiratory physiologists refer to the ratio of carbon dioxide produced to the oxygen consumed under such conditions as hyperventilating, but more so physical activity where we're talking about vigorous intensity, as respiratory exchange ratio. And it computes in exactly the same manner as the respiratory quotient. An increase in the respiratory exchange ratio above a value of 1 cannot be contributed or attributed to foodstuff oxidation. So typically, guys, respiratory quotient, the respiratory exchange ratio are utilized maybe more by researchers. When we talk as a class, when I teach this to students, even really honestly to graduate students in a laboratory or clinical setting that are doing research, when we look to understand values associated with aerobic energy systems, we look at something called a VO2 max or VO2 consumption. So the VO2 represents the greatest amount a person can use to produce ATP aerobically per minute, the greatest amount of oxygen that they can use. So this is a fundamental measure in exercise physiology. It is the standard to compare performance estimates of aerobic capacity, endurance, fitness. And that's another reason why I don't want you to get so completely wrapped up and confused about respiratory quotient and the respiratory exchange ratio, is because the predominant value or unit that we really look to understand in regards to the aerobic system is a VO2 and something called maximum oxygen uptake, or otherwise known as a VO2 max. And we perform these types of tests, whether it be a 1-mile walk test or a 1.5-mile run test or any sort of bench step test like the Queen's College step test or the cycling ergometer assessments or any type of swimming. Usually 9 times out of 10, when you're done with the assessment, the prediction formula that you will use will ask you to equate or to calculate their VO2 max. Maximum oxygen uptake can be very different for men and women, and also in different sports. Usually Olympic caliber athletes will have very different scores as compared to their less healthy, more sedentary counterparts. That's a graph that you can see here when comparing men to women. So I know you can't see this, is kind of cut off at the bottom, but numbers reflect maximal oxygen uptake in milliliters per kilogram per minute. This is VO2 max scores down here at the bottom. So you can see for women, sedentary individuals usually average, maybe in the 40s. If they're very sedentary in nature, it could be even less than a 40. And then we can see here, you can kind of see moving it through these different sports too, what energy systems are predominant. So we have fencers, typically score, between 40s and 50s, speed skaters between 50s and 60s scores, and then swimmers, runners, and cross-country skiers. You can see usually our elite female athletes will score between 60 to a 70 VO2 max, and you can see that for men it's very, very different. There are some individuals, elite trained athletes, that can score a VO2 max through indirect telemetry measurements or through prediction equations in the 80s or 90s. So typically when you're looking at VO2 max, it's on a scale from 0 to 100. And honestly, most of the scores that you will see, even for very sedentary populations, won't fall much below the 30s and won't be much out of the 50s or 60s. So that's just kind of a general point of reference when you're asked to calculate VO2 max. So what is the criteria for VO2 max? There's a couple different points that I want to hit home with you for this particular slide. when we're doing an assessment that's being measured, we're looking at something called a peak oxygen uptake, and this is a leveling off or a peaking over in VO2 consumption despite increasing intensity or effort within their work. So this is the max criterion is not met, or when local muscle fatigue, rather than circulatory dynamics, limits someone's test performance. So this is when they cannot work any harder despite increases in intensity. There are additional criteria for establishing a VO2 max, including 3 metabolic and physiologic responses. So they're listed for you here. The first one is a failure of VO2 versus intensity to increase by a previous expected value based on observations, maybe with a particular previous test. It could also be because of blood lactate levels. Maybe they're between 70 to 80 milligrams per 100 milliliter of blood, or about 8 to 10 millimoles. Or another criteria for establishing VO2 max is the attainment of a near predicted heart rate max, or a respiratory quotient of greater than 1. When you go through your assessments class, you'll understand how careful we have to be when putting someone through an assessment and allow them to work near their predicted heart rate max. And if you know what that means, good. If not, you'll hear that in future classes, how careful we are when asking someone to work beyond what their 100% max capacity is. So again, the maximum oxygen uptake is that peak oxygen uptake. They can't take any more despite increased levels of intensity. And basically what that means too is fatigue has set in, and it might be more of an issue with circulatory dynamics that actually limits test performance. You can see that here in this particular graph. And this is a good visual representation of someone achieving their maximal oxygen uptake. So if you notice down here at the bottom on the x-axis, you can see the speed at which the participant is either running or cycling. I guess it would be running because you can see someone running in this graph. You can see the duration that that participant spent at that particular speed, and it also shows you the grade of the particular treadmill. So you can see within the first 2 minutes they're working at about a 4.8 speed. That's actually a little bit faster than I would actually warm up on a treadmill. But there's obviously certain protocol that are set for certain clinical assessments. But you notice right off the bat at 2 to 4 minutes, all of a sudden their intensity has upped by the treadmill grade, going up to 5.5%, and they've also been increased, almost doubled their speed. And so you can see a large jump from their resting oxygen uptake even up until minute 3, when their oxygen uptake is increased significantly because of the increase of speed and the increase of grade. And you'll see concomitant increases in speed and treadmill grade. And at this point, we can see that the uptake of the individual, obviously they're breathing in more as the intensity becomes greater and the demand on the energy systems kicks in. And eventually here at about, I would say maybe 10 to 12 minutes, we have this peaking off. This is the leveling off that we would see if you were able to work with some sort of equipment to test someone's VO2 max. For our particular instances on this campus, we'll utilize prediction formulas. We'll talk about that a little bit on later in the PowerPoint. But again, if you were able to watch a computer software system track oxygen uptake according to speed, minute, and treadmill grade, you would be able to visually see someone as they had this peaking effect, and could advise them if they were still continuing the assessment at this point for them to stop the assessment. How do we test someone's aerobic capacity, their energy system, when it comes to VO2 max? Typically, we put a participant through something called a graded exercise test, and that is what the GTX stands for. So whenever you see GTX in your textbooks, or maybe in a PowerPoint or in a discussion, that's what GTX is referring to. There are two types of graded exercise tests. One is considered continuous and one is discontinuous. So in the table below, you can see the average VO2 max for 15 college students during a continuous and discontinuous bicycle and treadmill test, and you can see the averages based on the participants. This is a list. I'm not going to describe every graph that you see here. I like this picture because it shows you different common treadmill protocols. There are a ton of them. Some of them that may sound familiar to you based on our assessments course is the bulk wear test down here in the lower left-hand side, the Astran rhyming test, the Bruce protocol, the Knofton test is also used. Again, just other common treadmill protocols that are graded exercise tests. The protocols are slightly different according to maybe the type of study that's involved, or maybe according to the different types of equipment that are present within the different facilities. Some factors that affect an individual's VO2 max has to do with the actual mode of exercise, hereditary, the individual's previous training state, actually current training state, their gender, body composition, as well as age. Exercise mode can really reflect the quantity of activated muscle. So this is why, again, the beginning of the chapter talked about specificity versus generality. Typically, runners will perform well on a VO2 max graded exercise treadmill assessment because they have a previous history and they've trained their bodies according to the muscles that give energy to the required movement of running. Likewise, a cyclist will perform well on typically lower body assessments, and it's because of the amount of trained muscle mass required of the sport or the mode required for the assessment. Hereditary is actually really interesting. So current estimates ascribe for 30% of VO2 max, 50% of your heart rate max, and 70% of physical working capacity is due to inherited factors, which is really interesting. This goes back to the concept of those type 1 and type 2 muscle fiber types. So if you have parents that were probably gifted runners, you may not be the best best basketball player. You'll probably inherit their similar muscle fiber type and probably be a really good runner yourself. Likewise, if your parents are excellent sprinters, or if they have high power output as weightlifters, you're probably going to be passed on those traits according to muscle fiber type as well. So heredity has a lot to do with your VO2 max as well as the mode of exercise. Training state, we can train VO2 max. It is very trainable. In fact, training improves from anywhere from 6 to 20%, with the largest improvements coming from the sedentary population. Gender, again, we've seen in previous pages and graphs that women's VO2 max is about 15 to 30% below men. This may have to do with a distribution of muscle mass, lean mass versus fat mass. We know that women carry extra adipose tissue because we don't have the hormone testosterone, and it's also our body's way of preparing us to create life. So that's going to affect our power output and a little bit of our VO2 max as well. And again, body composition, differences in body mass can be explained roughly 70% of differences in VO2 max. And age has a little bit as well. Our heart rate it changes as we age. If you notice on any of the cardiovascular equipment in a gym, whether it be the treadmill, whether it be a bicycle, you'll notice that the target heart rates go down as age increases. And so that affects VO2 max a little bit as well. Typically, you'll see VO2 max expressed in two different units. One is liters per minute. That's considered an absolute value. Most of the unit of measurement that we will use when we're talking about VO2 max in class is milliliters per kilogram per minute. So there are different ways to express it. Just be very careful. They also look at it according to fat mass, percent body fat involved as well. But a majority of when we will be looking up to classify someone's VO2 max, this is usually the unit of measurement that we'll refer to. So be very careful, pay attention. Your books may have both formulas to calculate an absolute value as well as a relative value. For our purposes in doing any sort of lab assignments or calculations, make sure that for whatever reason, if you accidentally use the formula for absolute value, there is a way to convert the liters into milliliters, and that is what it is expected for class. So you heard me talk about VO2 max predictions. Typically, laboratories, clinical settings have the equipment to take these indirect measurements through indirect telemetry, where they measure, your oxygen consumption and oxygen expiration. If you're in a more of a bachelor's degree program at a small not-for-profit university that doesn't have that type of money, those thousands of dollars to purchase that really expensive equipment, you're not out of luck. You can rely on VO2 max prediction equations to predict VO2 max based on a sub-max performance. So in other words, instead of making someone participate in a Wingate assessment, you can use popular assessments that are a little bit more accepted, especially with sedentary populations. If someone hasn't done a lot of physical activity before and you try and stick them on a Wingate, they will run screaming from the building and never come back. So you can use sub-maximal performance assessments in order to take the results based on maybe heart rate, based on maybe time of completion of test, to plug those numbers into a prediction equation and actually have a VO2 max within the right ballpark. Obviously, taking indirect telemetry to assess VO2 max is going to be more accurate than doing some sort of prediction equation. But you deal with what you can get, and if you're in a situation where you don't have the equipment and you can't afford it, then you have to rely on calculating prediction equations for VO2 max. The upside to that is that it's usually very easily administered. It can apply to a large group without requirement of this formal laboratory or laboratory setting. So some factors that contribute to someone's predicted VO2 max has to do with their body mass, their body composition in regards to fatness or adipose tissue, running economy. Of course, if you're going to have someone on a treadmill assessment, I'm hoping that they've done some sort of running before. And another factor that contributes is also the percentage of aerobic capacity sustainable without lactate buildup. In other words, how long can they go without fatigue setting in? And the clinical way of explaining that is how long can they be aerobically inclined before that lactate builds up, causes fatigue, and causes them to stop the assessment. We can do VO2 max predictions based on heart rate. So these are prediction tests used in linear relationship between heart rate and oxygen consumption for various intensities of usually light to moderately intense physical activity. It's important to note these prediction equations can cause their true VO2 max not to be accurately reflected. You've got kind of this window where a prediction equation based on someone's heart rate will fall between 10 to 20% of their actual VO2 max. So that's kind of a drawback about having to do a prediction equation, but if you don't have the equipment, if you don't have the access, that's what you have to rely on. It is suitable for screening, it is suitable for classification of aerobic fitness, but doing a prediction equations for research purposes is not acceptable. It will not be the best for the researcher to rely on simply using prediction equations because of the relative requirement of research to be as accurate as possible. So that's why there's some limitations in regards to these prediction equations. The linearity of the heart rate to VO2 relationship. There's a very similar heart rate max for all individuals or subjects. It's based on the Carbonin formula. Again, you'll hear that. You'll learn it in assessments. It's assumed that there's a constant exercise economy, and there's also day-to-day variations in exercise heart rate based on the individual, what they've consumed, what medications they're on, and things of that nature. So again, we can calculate prediction formulas. They're good in a pinch. They're good for screening and classification of the general population. But in regards to research purposes, for studies, for publications in professional journals, those individuals should have access to the technology, the equipment to do the actual measurements. And this also shows the difference between someone that's an endurance-trained individual versus someone that's untrained. Someone that's untrained will reach their heart rate max a lot sooner than someone that's endurance-trained. Notice, though, however, that their heart rate seems to kind of max out in the same area in regards to beats per minute. But when we see that max happen, then we have a predicted VO2 max of, according to the x-axis, for an untrained individual, about 3 liters per minute. And the endurance athlete hits their VO2 max, or sorry, heart rate max, much later, and they have increased oxygen uptake with about 1 liter greater. Also, guys, considering 4 limitations, the VO2 max predicted from a submaximal heart rate, again, oh, we talked about this already. That was a duplicate. Sorry, everybody. It falls within a true range of about 10-20% of their actual VO2 max. Wow, this is a repeat slide. I apologize, guys. We've already talked about this. But I do like this point here. Again, these type of prediction equations are good for general populations, great for health club facilities, great in personal training. Absolutely, that would be a great place to use the prediction equations. All right, so lots more information that was presented to you in Chapter 7. I highly recommend going through these summary bullet points. These bullet points are also pulled directly out of the end of your chapters in your textbook. I just like to bring it out here to give you one more place to remind you to read the information and get the most important points of the chapter. And this concludes our lecture for Chapter 7. Thank you.